Everyone, in this video we are going to cover B5 currents and circuits, and we are going to start with basics of currents. Okay, so a current is defined as a rate of flow of charge, and in simple words I can say that how much amount of charge is passing through a cross section of a conductor in a given time interval. So we can imagine electrons that are carrying certain charges with them through a cross section, and measuring how many electrons have passed through a cross section in a given time interval is what we call as current. Now, current is measured in the unit is ampere, and we can calculate using the formula current is equal to charge over time. Okay, now since each electron has a charge of 1.6 into 10 raised to minus 19 coulomb, which is the elementary charge, and let's say n number of electrons are passing through a cross section, so we can calculate total charge that has passed through in a given time interval as Q is equal to N equal. Then the device that uses current, that measures the current, is ammeter. Ammeter is always connected in series, and ideally ammeter has a zero resistance. So this is the series combination. Second basic concept that we will cover is potential difference. Potential difference is defined as work done per unit charge to move a charge between two positions or 2 points in a space. Okay, so this is in the presence of electric field. Okay, now potential difference is calculated using this formula, work done over charge, and this work done can be any change in energy. So it can sometimes be also be equal to change in kinetic energy, and this charge into potential difference can give you change in potential energy. Potential difference is measured in terms of volts, and potential difference is very general concept. In case of circuit, we refer to potential difference as how much energy is consumed across a component in a circuit. So potential difference can be easily related to energy used or energy dissipated or energy given in a circuit. EMF is how much is the work done to move a charge from one terminal of the battery to other terminal. Basically, in a circuit, a battery or a cell is a power source. In that case, what happens is like the charges are flown or charges are moved from one terminal to another terminal, and it takes certain energy. So how much energy that is possible to convert from chemical energy inside a cell to the electrical energy is electromotive force, but it is not a force. Don't get a misconception behind that. It is a potential difference between the terminals of the battery. The device that is used to measure potential difference is a voltmeter, and it is always connected in parallel with the component. And ideally, it has an infinite resistance, so no current passes through it. Okay, so no current is required to pass through a voltmeter to measure a potential difference between 2 points. So a voltmeter, what it actually is measuring, in simple words, it is energy used across a component or between 2 points. Okay, so here is an example. Imagine this is a circuit where I have 20 volts of voltage and I have two 5 ohms resistors. Now V1 is a voltage across this, and V2 is a voltage across this component. Okay, now what is the reading of this voltmeter? When a switch S is closed, then we will see that this 20 volts of voltage will distribute equally across 5 ohms, and we will get a voltage of the battery will be evenly distributed, and we will get 10 volts of reading. But when the switch is open, the terminals of the battery, terminals of the voltmeter are directly connected with the battery. Okay, so it can directly measure the potential difference across the battery itself. That's why it will measure 20 volts. So no current is passing through a component. It means no energy is dissipated, and thus the voltmeter directly measures the potential difference across the battery. While V1, when the switch is open, no current is flowing, so it won't measure any voltage across V1, and it is not connected directly to the battery. There is a gap here, so it won't measure directly the potential difference of the battery itself. So it will measure 0 volts, but when the switch is closed, it will measure 10 volts. Okay. Now we will learn about Ohm's law. This is a very important law. At a constant temperature, the potential difference across a conductor is directly proportional to the current passing through it. And we relate both these variables by a proportionality constant, that is R, and R is also known for as a resistance, which is measured in ohms. Now, what is resistance? So usually in a material, in a conductor, you will find a positive ions or sometimes called metal ions or lattice, and electrons move through multiple collisions through a lattice. Okay, so a resistance can be defined as amount of obstacles offered by the material to the flow of charge, and it also relates with the number of collisions that electron go through while it is moving through a material. We'll talk about the heating effect of a current. So whenever there is a current passing through a conductor, there are constant collisions with the electrons and the metal ions. Now these collisions are inelastic, which causes exchange of energies with the metal ions. Now, with the gained energy by the metal ion starts vibrating more, and the increased kinetic energy is related to the temperature of the conductor, which increases the temperature. So there are collisions, and that collisions transfers the energy with the material, and material starts vibrating more, increasing its temperature. Thus, a higher amount of current will cause a more frequent collisions and thus increases the temperature. This is called as heating effect of a current. We can also discover some graphs of ohmic conductors. So ohmic conductors are basically whose resistance remains constant. So you can see a straight line gradient passing through origin. So you can possibly get two graphs, V versus I graphs. In V versus I graph, the gradient of the graph is equal to R. So resistance of Y is greater than resistance of X because it has a higher gradient. Similarly, in I versus V graph, the gradient is 1 over R. So it means the resistance of Y is smaller than resistance of X. For non-ohmic graph, the resistance is not constant. It means the graph is non-linear in most of the cases. So we will take the first example as a filament lamp. For filament lamp, this is given a symbol like this. As the temperature increases, the current increases, the temperature increases, and temperature increases causes the metal hybrids to vibrate more. As they vibrate more, the chances of collisions with the electron increases. Correct? So thus the resistance of the material increases. Okay. Now, if I want to find for this kind of a non-linear graph, you can see that the gradient is decreasing. It means the resistance is increasing because in I versus V graph, we can see that the curve is bending. Now here you need to understand one more thing. If I want to find a resistance at a particular point P, I don't take gradient of the graph. That is completely wrong assumption here. What we can do here is just to find a resistance at P, we have to find a voltage at P and current at P. Okay, this is the only way to do it, and not to find the gradient of the tangent for non-linear curves. It won't work like that. Other two non-linear or non-ohmic conductors are like thermistors. The thermistor, as the temperature increases, the resistance decreases. For LDR, as the light intensity increases, the resistance decreases. Okay, so this is the graphs that shows the same. They have inverse relationship. Now we will look at few examples to completely understand how we will use those graphs in the questions. So in this question, what they have given a cell of negligible internal resistance and electromotive force of 6 volts and is connected to 3 resistors R, P, and Q. Now R is a ohmic resistor while P and Q have non-ohmic, and their I versus V characteristics is given. Okay. Now you can see that graph is non-linear. Now the current in P is given as 0.4 amperes. We have to show that the current in Q is 0.45 amperes. Now, how we will do that? Okay, so we can use the graph and we can use the circuit arrangement to determine that. So from the graph, what information we can get? for the P. So P has a current of 0.4 amperes. 0.4 amperes, when we have current, from the graph we can see that it is possible to have 0.4 ampere current flowing through P when the voltage across P is 1.4 volts. Correct? Thus, if the voltage across P is 1.4 volts, while the EMF of the cell is 6 volts, the voltage across Q will be 6 minus 1.4, that is 4.6 volts. This is what information we get for the voltage distribution that happens between both these resistors. Now, for 4.6 volts, the corresponding value of current through Q is, this is 0.45. So this is how we use the graph, and graphical analysis combined with the information about the circuits can build a lot of problem for us. Okay, we can solve them using both these techniques. Now, what are the factors affecting resistance? The resistance is dependent on length of the conductor. It is directly proportional. So you can have R1 upon R2 is equal to L1 upon L2. There's a proportional relationship. And they're inversely proportional with the cross-sectional area. So you can have a relationship like this. And most of the time, instead of giving you area, they end up giving you radius or diameter. So the relationship with the radius and the diameter is inverse, and it is given like this: R1 upon R2 is equal to D2 upon D1, the whole square. Okay, and this is very much important. Now we can connect all those variables by a resistivity of the metal. The resistivity is unique to a metal. So I can, for a given material, like with varying the length and the area, I can make different value of resistances. Okay, but what remains common is resistivity. So resistivity is measured in ohm meter, and it's calculated as rho is equal to RA by L. This is a formula given in data booklet, or we can write it as R is equal to rho L by A. Okay, what kind of a question is expected? See this example. A cylinder of copper with a diameter D and the length L has a resistance R. Now, what is the resistance of the copper when the diameter is 2D and the resistance is 2L? So what we can do here? Okay, the method one says that we can first write a formula R is equal to rho L by A, and instead of A I will write D square by 4. Now R dash is the new resistance. Instead of L I have written 2L, and instead of 2D I have written 2 square, that is 4 D square over 4. So 4 get cancelled. What remains is 2 by 4, that 2 by 4 which is extra. Okay, and this rho L by pi by D square by 4 is nothing but R. So this is R by 2. We can do it by this way, or what I like to do is work it out with the ratios. I know that the resistance is directly proportional to length and inversely proportional to the diameter square. Okay, so we will write it in form of a ratio. Substitute the lengths that have changed, substitute the diameters that have changed, work it out, and then we will get the resistance will reduce by factor of 2. Okay, now the next application is resistors when they are connected in series. Then the total resistance is R1 plus R2. Okay, now what we need to remember about this is that current passing through the resistors in series remains constant, and the voltage distributes such that the voltage is equal to the voltage available in the total battery. Similarly, with resistors connected in series, we need to know that the total resistance increases, hence the current drawn from the battery will be less. That is the basic general norm. The more the resistance, the less will be the current passing through it. So usually when we want to calculate a current passing through, as the resistance of the circuit changes, for the same battery, different amount of current is drawn. This is very much important. So if I change any small resistance in the circuit, different amount of current will leave the battery, and we can calculate the total current by taking total voltage over total resistance. The first step in any circuit analysis is to calculate the total resistance and then calculate the total current and then look after how that current distributes and voltage distributes throughout the circuit. Similarly, in resistors in parallel, you can calculate the total resistance by taking adding the reciprocals of the resistance. And when resistors are connected in parallel, the total resistance decreases and hence there is more current flowing through it. So the total resistance in this case will be lesser than even R1 and R2. Okay, so that's why it is lower value when you connect it in parallel. And in resistors in parallel, the current distributes across both the resistors while the voltage remains same. Is the basic analysis. Okay, we'll look at an example. Imagine we have this kind of a circular arrangement where we have 3 ohm resistor, 4 ohm and 12 ohm, and we have to find the voltage and current across each resistor. Now, what does the most student think? Like they can apply directly the Ohm's law V is equal to IR for each resistor and then calculate it. But that's not how it works. Usually what happens is like this voltage distributes across each and the current also distributes when it is uh, connected in parallel. So for first step, what we will do is to calculate the total resistance. The total resistance here, you can see that the 4 and 12 separately has to be calculated, and if we do that calculation, we will turns out to be 3 ohms. So 3 plus 3, we will get 6 ohms as a total resistance. Once we get the total resistance, I can calculate the total current that leaves the battery by taking total voltage and total resistance. That is 4 amperes what I get. Now 4 amperes is the amount of current that leaves the battery, but since there is no other path flowing through 3 ohm resistor, so 3 ohm resistor 4 amperes passes through. So we got the current passing through 3 ohm resistor. The next step is that let's say the current splits, because what has to do, current has to split. Let the current splitting be x amount in the upper part. Now the important thing is the amount of current that leaves the battery has to be the equal amount of current that returns back into the battery. So it means whatever the current here is, it has to add up to 4 ampere again. So here in the other section, let it be 4 minus x. Okay. So if the voltage across 4 ohms and the 12 ohms has to be same because they are connected in parallel. If x ampere of the current is passing through 4 ohms, then 4 minus x is passing through 12 ohms. Since the voltage are same, voltage can be calculated by taking current into resistances. So current is x, resistance is r, current is 4 minus x, resistance is 12. So solving this for x, we get x as 3 amperes. It means current through 4 ohms is 3 ampere, current through 12 ohms is 1 ampere. Okay. Now the voltage across 3 ohms can be calculated by I into R. So once we got the current through 4 ohms, then only we can calculate the voltage across it. That will be 12. And since that is 12, the other distribution has to be 12 as well. Okay. So this is how we basically analyze any particular circuit. Okay. One example that we will do. In a circuit shown, a battery has an EMF of 12 volts. Okay, and there are 3 identical resistors that are shown. Each resistor is 10 ohms. The resistor L is removed. What is the change in potential at X? What first we need to understand what is the change in potential at X. So potential at a particular point is different from potential difference. Let me explain you this. When we say battery is of 12 volts, it means this point is at 12 volts and this point is at 0 volts. Now, since this point is connected with this point directly, so this point ideally becomes 12 volts and this point becomes 0 volts. Okay. Now, since this is 10 ohms and this is 10 ohms, when two 10 ohms resistors, okay, or any resistor like R and R, which are connected parallelly, that the total resistance is usually R by 2. So we don't have to calculate. It is just that equal resistance. Okay. So if there are 3 like this are connected in parallel, then it will be R by 3 like that. So it is directly can be solvable. So in this section, the total resistance is like this, that is 5 ohms. Okay, then there is X, point X, this is point at 12 ohms, and then there is a 10 ohms resistor. Okay, now we need to know is that the the distribution. If the 12 volts is there, the distribution is such that we will make this three parts. Like there is a 5 ohm part, there is a 5 and 5. So across each three parts, 12 volts will be distributed. So across this part, it will be 4 volts, and 4 and 4. Across the 10 ohm resistor, we can think of this as 8 volts. Okay. Now, when we are talking about potential at a particular point, potential at X must be 8, so that the difference is 12 minus 8, and that gives us 4. Okay, so and the 8 and this point is at 0. So this is 8 minus 0, 8. So this is the potential difference. Well, these are the potentials at a particular point. So X was earlier at 8 volts. Okay, when L is removed, this circuit arrangement becomes 10, 10 each. And in that case, the 12 ohms has to distribute itself 6 volts each. And for that, this point is at 12, this point automatically becomes 6, and this is 0. So it means X has reduced from 8 to 6 potential at X. So here, the correct answer is decrease by 2 volts. So this is how we apply basic circuit analysis and Ohm's law by looking at how the current and voltage distributes. We look at different application. Okay. The last part of this video will be the electrical power, and then we will look at the application of this in the next video. So the electric power is very simple and straightforward. Electric power is determined by formula of P is equal to V into I. And we can also remember is V square by R or I square times R. Electric power can be also be given as power dissipated divided by time, electrical power energy dissipated divided by time. And power rating, usually sometimes they give you power rating like of a lamp. Power rating of a lamp is 12 watts, 24 volts. So this rating represents power dissipated across the component, and this represents operating voltage of the component. And remember, brightness of the lamp is related to the dissipated power. So there are multiple questions related to power as well. So this is what we have covered in the first part of this video. In the next part, we'll look at the applications of this. Okay, thank you so much.